All right, guys, today we're going to go over how to do TCP/IP networking in C++ in hopefully 5 minutes or less. So those of you guys at home, the demo I've taken here is from the Boost TCP iostream library. There's Todd Howard, of course. And let's get into it. So the simplest way possible of doing networking is, this is called the Daytime Client. Again, it's off the Boost website, is using what's called an iostream. You should not use this. Disclaimer, don't use this for any serious project. This is just, in my opinion, something that's good to get you into networking. It's a good place to start when you kind of level up a little bit. You're going to be using more of the ASIO stuff rather than the TCP Streams stuff. Okay, so this is the entire program. Header stuff aside, this is the entire program. And for those of you that don't know what argv and argc are, whenever you run a program, like vim client.cc, vim is argv square bracket 0, client.cc is argv square bracket 1. So an argc is how many command line parameters were passed to you. So this one needs 3. It's going to connect to a server. So the name of the program, I renamed it from Daytime Client to just Client. I can probably change the usage here to just Client. So you're going to type in Client, and then you're going to type in the host name, which is going to be localhost because I'm running the server locally, but it could be a server on the internet. And then something called a port. So every network server has a port that it listens on. And if somebody has that port open, you can't run your code on that port. It'll give you a permission denied or address already in use error, that kind of stuff. You also can't pick a port that has a low number. If you have a number below 1024, it's going to probably require root permissions, and you can't do that either. But this is how simple it is to connect to a server on the internet. So it creates an iostream object. I'm calling the socket S, or maybe they call it that. This is not my source code. And they're connecting to a host name on that port. If it returned false, boom, error, die. And then all we're going to do here is we're going to grab one line from the server, and we're going to print to the screen and quit. That's it. So it connects to the server. It loads from the network. Notice it's using getline. Like, it's not like everything that you guys know about like CN, cout, iostream, oostream. All of it works exactly the same way for an iostream. Okay, an iostream, TCP iostream works just like CN, cout. Double right arrow works. Double left arrow works. Everything you know about files and reading right to the keyboard and console works the same way over the internet, which is why I teach it. It's a very easy way to get started, and that's it. That's the whole thing. If an exception gets thrown, it throws an exception, and that's it. That's the whole client. Now, if we try running the client right now, client localhost port, I don't know, 2527509, connection refused because I'm not running the server currently. Okay, so I got to get the server open. I guess I can run that. If you want to run the server backgrounded, you put an ampersand after it. Ampersand means run in the background. And if I type jobs, you can see I've got the server running, and I can kill %1, and the server is dead now. Okay. Another way you can do this is you can run the server, hit Control-Z, and then BG to background it. Now it's running in the background, but it's easier to just type the ampersand to begin with. I could also type PS. PS shows me the processes I have running right now, and I could use that process ID also to kill it, and it's dead. Okay. This way, using jobs and just, one is probably easier than getting the whole process ID, but, you do you. Okay, anyway, so that's how you run the server in the background, like that. If you're trying to running it again in the background, it's going to give you an error that port is already in use. So you can't do it. You've already got the server running. And you will do this at some point. So now if I run the client, like that, boom, connects to the local host. The server creates a string, sends it across the network. We read it across the network, which is the current day and time. It is May Day on 2024, May Day. And the current time is 2:36:04. And let's take a look at the server. So the server has, I refactored a very small amount. I made a port, a decision I could put up there. And if any of you guys try running the server right now, it'll say address in use because I have port 27509 open right now. I've claimed it. Okay. So it's got a little function that just returns a string containing the current date and time. You don't have to use that at all. Here is the code to set up basically a server. So an IO context kind of manages all of the networking stuff for you. And then an endpoint kind of opens up, I don't know what the right way to explain this is. It's saying use TCP version 4 and open up port 27509. So we're going to listen on this port, basically. And an acceptor basically accepts connections from clients on that port using TCP version 4. Now, you could also use TCP version 6. That's fine. Don't ask anyone what happened to TCP version 5. We don't talk about that. So this is an infinite loop. It's I usually use while true. Some people like while 1. These people like 4 crying emoji. All right. So, right? Crying face? No. Okay. And then it has the exact same code here. So it creates a TCP IO stream. That stream thing you can read to and write to, just like you do C in and C out. So when somebody connects, rule number 1, we never talk about TCP version 5. Exactly. Just don't talk. We don't talk about that. It was a dark period in the 90s. But any day now, TCP version 6 will become the standard. Any day. We've been saying that for 30 years, but any day now, it'll become the standard. So that's how you accept a connection right there. So you say acceptor.accept. And so that accepts the connection from the client. And then it will print a string to the client. And then it disconnects the client. When we get to the bottom of the scope, that goes out of scope. It closes the connection automatically. That's it. Very simple client server model. All right. And it works. Yeah. If you want to have multiple clients connected at the same time, well, it'll just personal connect. It sends one string and then it disconnects them. Like I said, don't use this if you're like Amazon, like your new internet Amazon. You're like, how do I make a server that handles hundreds of thousands of requests? Don't use this for that. This is the ground floor for networking. Okay. Now we can make it a little more complicated though. So we can make it a little more complicated. This is the entire program, right? This is a server, right? And you can actually see out anything you want. You don't have to have a function for it. You can just, and then when I say see out, I mean your double left arrow stream extraction operator, whatever you want to call it, stream insertion, whatever. You just double left arrow into the stream and it just goes over the network. It's that easy. All right. And so we can make it a little more complicated. So let's, could there be 2 different clients connecting to a single server? Yes, you can. The way that I would do it, if you're following this model, is I would spawn off a thread. Every time somebody connects, I create a thread, and that thread handles all communications with that client. That model works up to a certain point. If you have hundreds of thousands of people connecting, it's probably going to slow down. But again, I'm not giving you the top performance way of doing it right now. I'm trying to teach you, TCP quickly, and we're already 8 minutes in. But I mean, that's basically everything. But let's go ahead and modify now. So let's become Olson. Go into network streams demo. Go to server.cc. And let's see. Instead of this, let's mess with this. Let's take out their credits. They get no credits anymore. No Christopher Koloff. No. This is my copyright. Okay. All right. So let's pick a port. Luke, give me a port that you want to be on. We don't need the daytime anymore. We don't need that. Who cares about daytime? Who cares about daytime? Just enter a command. 171. You cannot do 171. Let's try 171, and I will show you why you cannot pick 171. Okay, so we'll try make. Boom. Look at that compile speed. Look at that compile speed. By the way, they upgraded our server. We got 8 cores down, 16 gigs. Yeah. And look at that compile speed. There we go. We're done. All right, so when we try running the server now, permission denied. You cannot connect to a low port number as just a regular normie on the server. So give me another port, Luke. 1710, got it. All right. So there we go. Compile. Perfect. So we're going to compile. We're going to go with a port above 1024. That should work. And server, there we go. Okay, server's running. Notice the server doesn't do anything. The server doesn't see in anything. It doesn't see out anything. The server, it talks to the network. All right. And so we can background it. Control Z suspends. BG runs it in the background. And now the client is going to connect to the local host on port 1710. Please enter a command. Boom. So it connected to the server. The server sent the string. Please enter a command. And now let's respond. So let's do a little back and forth here with the client. Now the client doesn't necessarily need to be multi-threaded because it's only talking to one server usually. But servers usually need to be multi-threaded or have some other system. There's polling and selecting and things like that, so you can see who's talking to you currently, but it's a little more advanced than what we're doing today. Easiest way is spawn a thread and just have that thread talk to that client. If there's any shared data structures, use a mutex lockguard to protect it. So, okay, so we are reading a line from the server. Please enter a command. All right, cool. We're printing it to the screen. And then we do something like, I don't know, cn into the line. Okay. We'll read just a word, and then we can send it back to them. So the socket is called S, and we will just send them the line back. All right. Boop. Goes over the internet. Easy as that. And then maybe we will, I don't know, read another line, and so we'll see what the server responds to us. You see, it's kind of like a tennis match or a game of volleyball. So the server starts off by sending the ball over, and the client prints it to the screen, reads a command, sends it back to the server, and the server is going to process the command like move north or move south or something like that, and then it'll update your position. But maybe there's a wall, and so maybe you don't move. You know, the server has to validate it. Servers should never trust clients in video games, right? They will lie to you. And so if you try moving through a wall, the server's got to be like, no, you can't move through a wall. But in general, you know, the person could give a command, and the server like updates your position, sends back your new position, the client redraws the screen. That's all it takes, really. And so you just have this basically in a loop until you get a command to disconnect or something like that. So yeah, I'm just going to do one back and forth, but basically you just do this in a loop. And then server here, again, this should be spawned off onto its own thread. You can look at the threads lecture from last week on how to do that. Okay, so we're going to enter a command, and then we're going to read. We're going to read a command from the user. So, I don't know, string, why is the formatting around the string? Sure. Why is the formatting all screwed up? GG was capital G. Weird. Okay. Okay, so we will stream, double right over into stream. Doesn't this look like, I don't know, reading from a file, right? Doesn't that look pretty much like you're like reading from a file, except it's reading from the internet? Yeah, you guys see that? It's like, that's all it takes. You know, you can mess up, and if you screw up, like if you do 2 reads and the client only sends 1, the server's going to hang, right? Because this is not multi-threaded. So, you know, you're going to be in trouble. And in fact, while it's waiting for the client to send something, nobody else can connect to the server, right? This is, again, this should be multi-threaded, but that's a demo. And so that's it. That's all it takes to read from the internet. And then we'll do some things like if the string is like, I don't know, north, you know, like we can have like some sort of variable or something. 0 equals 0, y equals 0. I don't know. This north would be, I don't know, y plus plus or something like that. And then be like, I don't know, see how their position is y. Something like that. And then we can do the same thing for north, south, east, west. I'm not going to bother belaboring the point. So basically, if we do this right, the client can give commands to move north and south and east and west, and the server will update their position and, you know, obviously check to see if you ran into a wall, if there's a monster, et cetera, et cetera. So is the server currently already in use? Good. So this is something you're going to encounter. You're like, oh shit, I forgot to kill it. How do I kill it again? Jobs will list the number of jobs you have open. Job number 1 is the server. So job %1 will kill it. Alternatively, PS will give you the process ID of the server, and you can kill it that way as well. Either way works. So either that kill or that kill will kill the server, then you can launch it again. Now, sometimes you'll run into a problem where if somebody's communicating with a server and you kill it, sometimes that socket will stay open for 5 minutes. So having the ability to quickly change the port you're on will make your development process a lot more fast. If you are in fact, if there's data in transit, then in order to make sure there's no old connections, the operating system will leave that socket open for 5 minutes, even after you've put the program. You can't launch your program again for 5 minutes. So just be careful of that. Okay, server, and then I'm going to background it. Then let's run the client. Okay, please enter command north. Your position is now x01. Boom. Simple as that. Yeah. And so we sent a command to the server. The server updated the x and the y. Sent a update. You're now at this location. And all we need to do is put that into a loop. And we've got a multi-computer game, although it's really on one computer right now. You know, the client and the server don't have to be on the same machine. Like I could be running the server on Erudite, which is the name of our old server, and this could be running. The client could be running on Univac, which is the name of the new server, and you would type in like client, erudite.csci4x.com and port 27509, whatever. And so you could do this over the internet. Simple as that. That's it. And you can just build up more and more complexity from there. If you want to have multiple players, then you just need to spawn off a thread for each person and have a mutex protection. Again, see the lecture on multi-threading on how to do that. I'm not going to go over all of that again. So that kind of makes movement work in games stuff with updating the position constantly. Yeah. If you have a real-time game, you're just sending a packet, every update, like here's where I'm at, move. And the server's going to be sending back not just your position, but it's going to be sending back, oh, that monster over there, it's now closer. Oh, there's a fireball that just went off here. Spawn a particle effect here. And so the client will receive from the server an update from the server, and then it does its things and send a command to the server. Servers don't always update 60 frames a second. It might be like 10 ticks a second or something like that on the server to cut down on the bandwidth. But the client might be running at like 144 frames a second. It only get updates periodically from the server. And so you can have a separate thread on the client that all it does is talk to the server. And so every time the server sends a packet, it reads the data and then updates the globals, locks them down, mutex, lock guard, boom. And then, okay, the monster's position is here now, your position's here, et cetera, et cetera. And then the clients will do things like client-side prediction. So instead of seeing the monster go chunk, 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 because it only updates maybe 10 times a second, which would look really rough, what the client will do is it'll say, oh, well, it's been moving at 5 miles an hour towards me, so I'm going to I'm going to do interpolation. I'm going to predict it's going to keep moving at me at 5 miles an hour until I hear otherwise from the server. And so the client will actually interpolate between the server frames, guessing, like especially if the server says it's moving at 5 miles an hour in this direction, it can interpolate in between tick updates. And then there's a lot of tricks you do with compression and things like that. Like if you haven't moved, you don't need to send an update on your position, which cuts down on the networking that the bandwidth requirements needed. How does packet loss tie into it? So what we're doing here is something called TCP. You can't technically sort of have packet loss with TCP. What will happen is the connection will go down. Like if you lose connection, you lose the connection. And you'll get, I think, an exception thrown. Can't have packet loss. Everything you send will come in the order you sent it, guaranteed, when you do TCP/IP. When you do TCP transmissions, it is guaranteed to be delivered unless just, the network's gone down. If there's any connection at all, it'll reroute, it'll retransmit. The trouble is you get latency when you do that. So when you're doing video games, TCP is not actually the right protocol to use most of the time. Most of the time you want to use something called Todd Howard instead. Called UDP instead. And UDP is non-guaranteed. It's non-reliable. The packets you send might come in a different order than the order you sent them. And you can get packet loss. So if a router is busy, it could start dropping packets. Like, so you sent out 10 packets, and then one of them might, just get lost. And so that's a lot harder to deal with, right? Like, it's good because all that retransmission and things like that adds a lot of latency. When you're in a video game, think about it. Like, you're playing Call of Duty or something, like, and so the server sends out, hey, Comez is at location 10, 20, 30. X is equal to 10, Y is equal to 20, Z is equal to 30. And that packet gets lost. With TCP, what will happen is the client will detect the loss of that packet, and then it'll send a message to the server saying, like, hey, I lost the last packet, and then the server will resend it to you. But by that time, he's probably moved. You know what I mean? Like, he's probably not there anymore. Like, the amount of time it takes to, like, and it's like goes back and forth. It's probably out of date. Like, if you're doing video conferencing, I don't need you to retransmit, a data from a second ago. It's going to sound really weird having my voice lag out. Just drop the packet. You know what I mean? Just like lose the data. Like, I've been interpolating Comez's position all along. If I lose a packet, just keep interpolating. You know what I mean? Just like keep guessing. Like, the last I heard, he was over here. He was running at 5 miles an hour. I lost the server update. Okay, just keep guessing. He's moving that direction. And if he was moving that direction, you don't even notice it. Packet drops happen all the time, and you just don't even see it. When you do see it is when he unfortunately took that moment to backpedal. And so what you'll see is rubber banding. Have you guys ever seen this in a video game before? A rubber banding effect where you like go through a door and then you snap back all of a sudden. You're like, whoa. It's super annoying. But what's happening is that the client is predicting that, like you got through a door, but what happened was somebody shut the door and you didn't get that update. So it drew you through the door and you see all the people on the inside like, oh, hello, friends that are about to shoot me. And then all of a sudden the server like, whoop, and you're like, what? And you're staring at a door that's been closed because the server got the command to shut the door prior to you going through it. And then by the time it has synchronized everything up, you've snapped back like a couple meters. And you'll see people moving around. Like, you'll see them moving, and then you'll see them go, whoop, like they could just be standing there, right? They're not even moving. And when they rubber band, they go, whoop. Like, they're not walking. It's just the server is like, kind of catching up. And so, what about when you're walking forward and it still rubber bands? Yeah, it happens because it really depends on how talented the networking people are. Is really what it boils down to. It's really hard. It's really hard to write a networking protocol that handles packet drops, handles latency, handles potentially hundreds of clients, thousands of clients, like World of Warcraft, like you've got however many people playing in a world. So Blizzard will do things like do layers and instancy and things like that to try and cut down on it. Because if you have 5 people in a room, every time one of them moves, all the other people have to know about it. So you've got like an n squared problem. If you've got 10 people, that's like 90 connections. If you got 100 people, it's like 9,900 connections of updates that have to take place. So the more people that can see each other in the same multiplayer server, the bandwidth consumption goes up n squared. And even for a rich company like Blizzard, they do all sorts of tricks to try and cut down on the number of players that can see each other at one time. And so you might see your friend, like your friend might be in the same place you are and you can't see them. They're like, I'm in the Ogremar, auction house. Like, I don't see you, and then, then they, they fade in. So Yeah, all that stuff is, it's easy to be harsh on game developers because multiplayer sucks uh, in most games. Yeah, it starts running slower, sure, but I mean, there's also just more triangles on the screen. You got 1,000 people on the screen. That's 1,000 models that have to be animated and rendered and stuff like that. But it show some mercy to the game dev people because it's actually really hard to do networking correctly. It's really difficult. There's a lot of trade-offs that have to be made. That said, I will say Quake 1, Quake World runs on a modem. I'm just saying. Like the amount of bandwidth required per client, 10K. You need a 10K connection, and that's as smooth as anything will ever be. 10K connection from you to the server. Server handles 32 users. That's a whole whopping 320 kilobytes per second. And it handles 32 players. Somehow, Blizzard's like, Overwatch, 6 players per side, too much. So we're going to cut it to like 5 players because there's too many people. And I'm just like, bro, we had 32 players, 16v16s, back in the day. Why is it impossible? Everyone's got a cable modem now. You know what I mean? Everyone's got either like fiber optic or cable or like whatever, DSL kind of thing, AT&T sells. How is it that in this world with high-speed internet, we can't do 32 player games anymore? I don't know. I'm going to toss that one out there. Like somehow back in the day, the people that did software were able to figure it out, and nobody's been able to figure it out since. There's been very few games that I can think of that support 32 players. Like Blizzard used to have 50-man raids, and they don't do that anymore. So Battlefield, yeah, Battlefield would be one of them. Sure, yeah, 64 is still the max, right? There's one game that came out from Sony that had 128-man teams. And it came out 15 years ago. I don't remember the name of it now. That one was fun. That one was really fun. Blizzard's just greedy. I don't know. I don't get it. Why is the experience better with less people? I don't necessarily think so. So, what was the name of it? It was a Sony. It's a Sony PS3 game, 128 players, something like that. Mag, that was it. Yeah. Came out 2010. Yeah, 256 players, 128-man teams. It's really fun. It's actually really fun. So, yeah, that's you can get a job just being a network specialist, where you just work on the network stack. And when you do so, you're going to do more than this. This here is super Fisher Price, babies first, network connection. But it gets your foot in the door. It gets you going. Look into Boost ASIO. That's basically what most people use today for actual products and things like that. But the TCP stream is good for you guys because it looks just like CN, cout, iostream, stream, right? No, is there no stream? An iostream implies the existence of an stream, right? No, not how I feel now. All right, so that's it for networking. Now we're going to switch over to DRM GUI. And Olson, that source code's yours now.